Okay, so some of this has been covered in class, but we're going to put all the examples in here so that you can see them. And we're going to go ahead and talk about uniform motion. So uniform motion means motion that's occurring at the same rate over your time. So with motion like this, we can do distance equals rate times time. Okay, this formula that you've used before. Because the motion is uniform. So I'm going to go through the examples. You can skip any of the examples that we did in class, and then you can skip to the ones that you need. So this one says an airplane flies 1,000 miles due east in 2 hours and 1,000 miles due south in 3 hours. What is the average speed of the plane? So average speed is kind of setting up that uniform speed. So this plane had two different speeds at two different times because the 1,000 miles was achieved one time in 2 hours versus the next time in 3 hours. But average speed is just saying, tell me the speed in general it took you to make the trip when you just look at how long you went and how much time you took at. So speed here is going to be in miles per hour. And so we basically want to find out what was the total amount of miles that we went and divide it by the total amount of time. So you can see this with the distance equals rate times time, that you flew a total of 1,000 miles here and then another 1,000 miles here. So you flew 2,000 miles total. You don't know which rate at because you're trying to find the average speed. And the time that you accomplished this in was 2 hours and then 3 more hours for a total of 5 hours. And then you can solve this for the rate. And then you would get that the rate is equal to 400. And again, this was miles and hours. So this is 400 miles per hour. Okay. So for the next problem, to try this, it says Lisa and Michael traveled 2 miles in half an hour. What was their rate? So again, so we have miles, which is a distance. So we have 2 miles. We don't know the rate, and this was accomplished in half an hour. And so then here we would also solve for rate. In this case, I would times by 2 to cancel out the 1/2. And so I would have that the rate is 4. In this case, meaning the rate is 4 miles per hour. All right, so the word problems we're going to do here are going to seem kind of silly. These are almost like the algebra problems that people make fun of all the time, like train A leaves the station at this time, train B leaves the station at this time, when will they meet each other, and people are like, I would never calculate that. And I totally agree. Really what we're looking at here is there are other applications of distance, rate, time in science, but we don't all have like the same science background or stuff like that. And so what we're going to do is use these problems as models, even though they seem a little silly, so that later in your career, you can apply them to different topics where distance, rate, time is relevant because it's a different type of uniform motion problem. So try to understand that we know you might not calculate this in real life, but you may use this in a different application later on. So Mr. Williams and Miss Tran leave their home at the same time, traveling in opposite directions. So I'm going to make myself a little picture. It might seem silly, but it will help me kind of understand what I have to do. So Mr. Williams and Miss Tran leave their home same time, going in opposite directions. Mr. Williams travels at 80 miles per hour. Miss Tran travels at 72 miles per hour. And how many hours will they be, 760 miles apart. So there are 2 different distance, rate, times happening in this problem. Okay, there's Mr. Williams and there's Miss Tran. Okay, so when we look at Mr. Williams and we want to put in the distance, rate, time, it doesn't say specifically his exact distance. So I'm going to call that distance and I'm going to put a little W with it. So I know that that's Mr. Williams' distance and it's not necessarily the same as Miss Tran's distance. We do know his rate. It specifically said he traveled at 80 miles per hour. And we don't know how long he was traveling. So we're going to go like this. And then we could write a similar equation for Miss Tran. And so we would have this, which right now these two equations by themselves, they can't be solved because they both have two variables. And even together, they can't be solved because the D's and the T's are not the same. They're different. One is a distance for Mr. Williams. One is a distance for Miss Tran. Same with the time. So what we want to do is try to relate the distances and the times together so that we can understand how they are and write them with the same variable instead of having like an equation with two variables, another equation with two different variables. So two equations in total, but with four different variables. That's a lot going on. So we're going to go back and see if we can understand anything from the problem that gives us information about the distance or about the time. Okay. So first it says that they leave their home at the same time. So they left at the same time, and this problem will cause them to end at the same time because we're trying to see when they are 760 miles apart. So when they're 760 miles apart, no matter who's gone further or anything like that, that's when the problem's done. And they would have started leaving at the same time, and then the problem would abruptly stop at the same time. This means that, so the same time means even though I marked them differently in my equations, the time that Mr. Williams on the road is the same as the time as Miss Tran, and I'm just going to call that T now in my problem. So that helps a little bit. That takes out one variable because now the time is just T. There's not two different times that I'm dealing with. Then I look at the distances. The thing that's on here about distance is this 760 miles apart. It says, when will they be 760 miles apart? So I know that I want the total distance to be 760. And this is where the drawing comes in handy because it would matter if they're going the same direction or opposite directions. Since they're going opposite directions, to reach that 760, that would be the distance that Miss Tran traveled added with the distance that Mr. William traveled to make the total of 760 miles. So in this problem, for the total distance to be 760, it would be the two distances being added together. Okay, so what that tells me is I can replace Mr. Williams' distance with the 80t that I know it's equal to. I can replace Miss Tran's distance with the 72t that it's equal to. And I now have an equation with only one variable. So again, look what I did. I used distance, rate, time to look at Mr. Williams' situation and Miss Tran's situation. I saw there were too many variables, so I tried to find relationships between them. So the first relationship I saw was that really the times were the same. So that allowed me to use the same t in each equation. The second relationship I saw was the distance adding up to 760, which essentially gave me this solvable equation right here. So this will say 152t is equal to 760, and then I can finish solving this by just taking 760 and dividing it by 152. And I get 5 when I do that. So don't stop here, go back, see if you'd answered the question and what the answer really is. So it says, in how many hours? So this is what I should be answering. In how many hours? So then look at what you got. It's a T. T stood for time, so that makes sense. And we originally put time in hours. I know that because our rate was miles per hour. So this 5 does represent a number of hours that they've both been traveling. So the answer here would be 5 hours. Okay. So I'm going to look at the try this. It's really similar. So this says, suppose John and Gina leave the same time traveling in the same direction. So the picture looks slightly different. This time you'd have John and you'd have Gina traveling in the same direction. Gina drives at a rate of 85 kilometers per hour. John at 70 kilometers per hour. How long till they are 90 kilometers apart? I'm going to change my picture because it just bothers me that I put the faster person behind when they would be in front. Okay, so again, there's two different rates in this problem, two different situations. I have John and I have Gina. John is going 70 kilometers per hour, and Gina is traveling at 85 kilometers per hour. So notice I almost write their equations exactly the same as last time. I have their rates, but I don't have any specific information about the number of hours or the exact distance that either person traveled. And so I'm going to look for the same things as last time. I'm going to go back to the problem, and I'm going to look for things that tell me something about the relationship between time and distance. So again, in this problem, they left at the same time, and the problem ends when they're a certain amount apart. So they would both be on the road the same amount of time. So since they left at the same time and the problem will end at the same time, this means John's time is really not any different than Gina's time, and I'm just going to decide to call time t. So I'll adjust these equations a little bit just like I did last time. The other thing I want to know about is if I can relate the distances together, because those are two different distances. And what I know about distance here is that I'm seeing how long until they are 90 kilometers apart is when this problem ends. So what does it mean in this problem for them to be 90 kilometers apart? When I look at the picture, this is how far John and Gina are apart. And that distance would be Gina's distance minus John's distance. And that would give me this difference in between them here. So apart in this case would be the faster person minus the slower person, because that would tell us how much ahead of him she is. And we want her to be 90 kilometers ahead of him. And so now, just like last time, I can substitute in, and it will help me because then I'll only have one variable. Oops. So this will say 85t minus 70t equals 90, which is 15t equals 90. And when I divide that by 15, I get that t is equal to 6. And then again, think about what you've just found. So t for us was a time. Given that our rate was in kilometers per hour, this is hours. And I want to go back and see if that's the answer to the question they were asking me. So the question was how long until? And they both started at the same time, so they've both been gone. This means for 6 hours. And that answers the question that they were asking. So the answer will be 6 hours. All right, for example 3, it says at 8 a.m., Stephen leaves home on a business trip, driving 35 miles per hour. Half hour later, Angie discovers he forgot his briefcase. She drives 50 miles per hour to catch up with him. She is delayed 15 minutes with a flat tire. When will she catch up with Stephen? So two people again in this problem. There's Angie and there's Stephen. And I don't know how far Stephen's gone. I know his rate is 35, and I don't know for how long he's gone. I don't know how far Angie's gone, but I know that she's driving at 50 miles per hour, and I don't know how long Angie's been gone. So again, in order to solve this problem, I need relationships between the time and the distance. So when I look at the time, this time they did not leave at the same time. Angie left a half hour later, and she was also delayed 15 minutes with a flat tire. What this means to me is that when I think distance, rate, time, you have to remember in that distance, rate, time equation, this time is supposed to be the amount of time the person is traveling at that rate. So Steve has been on the road longer than Angie. Okay, so Angie's time is 45 minutes less than Steven. And I know this because remember, time is how long you've spent on the road. She didn't leave till a half hour later than him, and she was stopped for 15 minutes with a flat tire. That's 45 minutes total that she was not traveling at all at that rate. So the way that I would write this is that Angie's time is 45 minutes less than Steven's time. Remember here, we kind of want time in hours because our rates were miles per hour. So I'm not going to write 45 minutes. I'm going to write like 0.75 or 3/4 because that's how much 45 minutes is of an hour. Okay, so this helps relate the times together. Okay, so this means I can change Angie's equation. Instead of having Angie's time in it, I can have Steven's time minus 0.75. So I'm closer to being able to solve these because now I've narrowed it down to 3 variables, Steve's time and then their individual distances. So then I want to see if there's anything in here about distance. And then what I see about distance is that this problem ends when she catches up with Steven. So think about what this means in the picture. Steven's ahead, he's going. Angie's driving faster, so eventually she catches up with him. And so what that would mean is that their distances are equal. They both left home, and then they both ended up at the same spot together. And so for distance, what I can see is that Angie's distance and Steve's distance will be equal when this problem is done. Okay? So Angie's distance right now we have represented as this expression, and Steve's distance we have represented as this expression. So I'm going to set them equal, and notice the only variable I have left right now is time. I kept that little s with it to remind me that if I solve for this time, this is the amount of time that Steven's been gone from the house, not necessarily Angie. So I'm going to distribute this 50 so that I can try and solve this. So I'm going to do 50 times 0.75. That gives me 37.5. I'm going to combine the variables onto the same side. So this gives me negative 37.5 equals negative 15 times the time. And so then I'm going to divide by negative 15. And get 11.25. Oops, sorry, that's not right. Sorry, 2.5. That came from. All right, now remember what I've just solved for. I solved for a time. It specifically is Steven's time, and it's 2.5 hours. I'm going to go back and see what the question asked, okay? So the question asked, when will she catch up with Steven? Since they gave me a time in this problem, I'm going to use time because they both left at different times, so it's confusing to say like after 2.5 hours. So Steven's been gone for 2.5 hours, and here it says he left at 8. So that would mean 2.5 hours later would be at 10:30 a.m. You could also say 2.5 hours after Steven had left, or you could give it in Angie's time. You just would have to make sure that you're identifying whose time that you're giving information about. All right. For the try this, James left home on his bicycle for a long distance ride. Sydney left 3 hours later on her motorcycle carrying his lunch. So James leaves. Later, Sydney leaves. Sydney's traveling at 42 miles per hour. Okay. Then it says she caught James in 1.5 hours. How fast was James traveling? So we have two people, again, two different rates. We have Sydney and we have James. Okay. So Sydney, it doesn't tell us her distance. We know she was traveling at 42 miles per hour and we don't have her time. James, it doesn't give us his distance or his rate or his time. So let's go and try and find some relationships in this problem. So first, for time, I see in here that Sydney left 3 hours later on her motorcycle carrying his lunch. So Sydney is 3 hours on the road less than James. Okay. So Sydney's time is James's time minus 3 hours. She's driving at that rate less time. So I can change her equation slightly to replace her time with that expression. Okay, now they're a little bit closer. Then I see that it says she caught James. So this tells me something about the distance. They both left the house and eventually she caught up to him. That would mean her distance and his distance would have to be the same at the end of this problem. So Sydney's distance and James' distances are equal to each other. So that would give me, this. So here's Sydney's distance that we have, time James minus 3, and James's distance, which still looks a little bit messy because we still have two different variables in it. So do we know anything else when we look at this that we haven't used? And when we do, it says right here, she caught him in 1.5 hours. So they actually do tell you her exact time. Sydney spent 1.5 hours on the road. That's the same as saying that James spent 4.5 hours on the road because she was 3 hours less than him. So we know that we can plug in 4.5 for James's time and have something like this, which means we're able to solve for James's rate by dividing both sides by 4.5. So I am going to go ahead and do 42 times 1.5 and then divide that by 4.5. And so I get 14. So I get that James's rate is 14, and that would be miles per hour. And then I want to look back and see if that answers whatever it is they're asking me. The question was, how fast was James traveling? So that does answer the question they asked. He must have been traveling at 14 miles per hour. All right, example 4 says the soccer team is holding their annual car wash to raise funds for club projects. Olivia can wash and wax one car in 3 hours. George can wash and wax one car in 4 hours. If Olivia and George work together, how long will it take them to wash and wax one car? So this is a little bit funny because people's original instinct sometimes is to say like 7 hours. But if I can wash a car in 3 hours and someone helps me, even if they're very slow, it should lessen my time below 3 hours. So right now, I at least know that if they're working together, it should take less time than the fastest person. So we can't add times together in this case. What we could add together are rates. And so I want you to look at this. You might think this doesn't look like a distance rate time problem because it doesn't say like miles per hour or something like that, but it is like cars per hour. Like how many cars can they wash in 1 hour? So really your distance here, your distance is like how many jobs they can complete in that time. So here there's two people. There's George and Olivia. And so it says Olivia can wash and wax one car. So the distance or the amount of cars she complete is 1. We don't know her rate, but she can do this in 3 hours. So this does eventually allow us to solve for the fact that Olivia's rate is 1/3. She can wash 1/3 of a car per hour, where George can wash and wax one car in 4 hours. So George's rate is 1/4 of a car per hour. if Olivia and George work together. So this means I need to find their rate together. And rates we can add because this now means Olivia's getting a third of the car done in an hour. George is getting a fourth of the car done in an hour. If she's doing a third of it and he's doing a fourth of it, then in 1 hour, 1/3 plus 1/4 of the car will have been washed and waxed. So their rate together is 1/4 plus 1/3. I'm going to make common denominators here. So that's 3/12 plus 4/12, which is 7/12. Okay, that's their rate together. And the question about them is about together. And now I'm going to go back and look at the question. It says, if Olivia and George work together, how long will it take to have them wash and wax one car? So I have not answered that question. I know their rate is 7/12. That is not how long it will take. So I am going to set up an equation specifically for them working together. The distance is one car. That's how much we want them to complete. I know their rate is 7/12. I need to solve for the time instead of the rate. In order to solve for the time, I'll multiply by 12/7. And I get that the time is equal to 12/7 or 1 5/7 hours. So my answer is 1 5/7 hours. All right, so looking at the try this, a very similar situation. Jan can paint a chair in 45 minutes. Jeff can paint a chair in 35 minutes. If they work together, how long will it take them to paint 6 chairs? So we have Jan and we have Jeff. So it says Jan can do 1 chair in 45 minutes. I'm going to use the last letters of their name because I don't have it. If I use 45, it's okay. I just have to understand that I'm now changing times to minutes. So this means Jan's rate is 1/45 of a chair per minute. And Jeff can do 1 chair in 35 minutes. Which means Jeff's rate is 1/35. The question asks about them together, so I'm going to take those two rates and use them to find a rate together. So their rate together would be 1/45 plus 1/35. So I'm going to make a common denominator, and I'm actually going to do what we did previously. So 45 is like 3 times 3 times 5, and 35 is like 5 times 7. So my common denominator would have to have a factor of 5, a factor of 7, and 2 factors of 3. So 35 times 9 is 315. So 315 is the common denominator. And 45 had to be multiplied by 7 to get that. So that's 7 plus 35 in order to get 315 had to be multiplied by 9. 9. So this is 16 over 315. So then it says, how long will it take them to paint 6 chairs? So they didn't ask for their rate, so I'm not done. So I'm going to take their rate and try and solve for a time, since it said how long will it take them. And it said 6 chairs. So the number of jobs or the distance is like 6. The rate is 16 over 315. And I'm looking for the time. So I'm going to go ahead and multiply by the reciprocal to solve this equation. And then I'm going to just kind of reduce that as much as I can. So 6 and 16 are both divisible by 2. So this gives me 315 times 3, which is 945 over 8, which is 118.125 minutes. Or if you wanted to convert that to hours, since it's a large number, you could divide it by 60 and you could get almost 2 hours. Okay, looking at the last example, we have Sally and her brother rented a boat to fish in Jones Creek. The maximum speed of the boat in still water is 3 miles per hour. At this rate, a 9-mile trip downstream with the current took the same amount of time as a 3-mile trip upstream against the current. So the two situations here are the downstream and the upstream. And the way that this is going to work is that their speeds are going to be different. The boat speed is constant, okay? The boat speed is 3 miles per hour. But when it's getting downstream, it is getting plus a push from the current. When you're going upstream, you're working against the current, so the current's slowing you down. So the rate for downstream will be the boat speed plus the extra push of the current, and the rate for upstream will be the boat's speed minus the strength of the current. So for the downstream trip, it says a 9-mile trip downstream. So 9 miles was the distance downstream with the current. So you have the rate here is the boat plus the current. And we don't know how much time it took. And then it says a 3-mile trip upstream. And that's against the current. So that's the boat speed minus the current. And we don't know how much time that took. So again, we have two equations. If they had the same two variables, we could solve a system. But right now they have 3 variables. And it's these times that are different. And we don't know their relationship. So what we want to do is see what do we know about the time. And so here it says the trips took the same amount of time. So if the trips took the same amount of time, that means the time to go downstream is equal to the time to go upstream. And so I can actually solve this equation for the time to go downstream and just kind of rewrite it. And same for the one about going upstream. And now I can set those quantities equal to each other since those times are equal to each other. Okay. And then I would want to solve this by multiplying everything by the least common denominator to cancel out the denominators. And so that would leave me with 9 times 3 minus c and 3 times 3 plus c. And so this is 27 minus 9c equals 9 plus 3c. And I'm just going to continue to solve this equation. So I would get that 12c is equal to 18. And that c is equal to 3 over 2. So remember what c stood for us. C stood for the current, and that was specifically the rate of the current. So I'm going to look back and see if I've answered their question. It says what was the rate of the current. So they were right, and our speeds here were units of miles per hour, excuse me. So 3 over 2 miles per hour, or 1.5 miles per hour, would be the speed of the current. So this last try this says an airplane in calm air can fly at a rate of 500 miles per hour. It can fly 2,575 miles with the wind in the same time that it can fly 2,425 miles against the wind. So our two scenarios here where the rate changes is when the airplane's with the wind, because it's the airplane's rate plus the wind, versus when it's against the wind. Just like the current, that would slow the airplane down, so it would be the airplane's rate minus the wind. So we know the plane can fly at 500 miles per hour. So when we're talking about the trip with the wind, it says right here we can fly 2,575 miles with the wind. So 2,575 miles with the wind means the airplane's rate plus the wind. And that's the time for the trip with the wind, which we don't know exactly how long that took. It then says we can fly 2,425 miles against the wind. So 2,425 equals the airplane speed minus the wind. Oops. And that is for the trip against the wind, so whatever time that takes. So just like last time, it's close, but there's 3 variables here instead of 2. So we want to find some relationship between the time. So I look back in the problem, and it says it could fly so many miles with the wind in the same time that it can fly the amount of miles against the wind. So that means our time with the wind is equal to our time against the wind. And again, we have things that we can substitute in for that equation if we rewrite these equations. So for time with the wind, I'm going to substitute in this expression. And for time against the wind, I'm going to rewrite that equation and substitute in that expression. And again, to solve this equation, I would want to multiply by the least common denominator. So that's a factor of 500 plus W as well as 500 minus W. On both sides of the equation. Canceling out one of the factors on each and then leaving us with some rather large numbers to multiply. So then I'm going to go ahead and combine some things so that or distribute some things so I can combine like terms. So 2,575 when multiplied by 500 gives me 1,287,500. And 2,425 multiplied by 500 gives me 1,212,500. And then when I move things around here, so I'm going to move the whole numbers by canceling out some of them to one side, and then the ones with W on the other side, I will have 75,000 is equal to 5,000 W. And then when I divide both of those by 5,000, I get 15. So then remember what W is. W is the wind. So that's the rate of the wind, and that would be in miles per hour. And it said find the speed of the wind. So speed is rate. So the answer here would be 15 miles per hour. So the goal here was for you to get the examples so that we can answer some questions next time, and then we can attempt some of the problems in class.